All right, hey guys, welcome back to another video. So this week I'm going to be talking about the Riemann sum, right? So first of all, let me start off with the graph of a function, right? So the Riemann sum is just another way to kind of take the definite integral without actually taking the definite integral. I'll explain more about that in a little bit, but so like let's say I have this function right here. Okay, and I want to take the definite integral from here, we'll call this -5, and to here, right? So I want to take the definite integral of f of x between -5 and 5, right? So this is another example of a case where I can't just make this definite or this area under the curve be like a shape that I know the area formula for. But what a Riemann sum does is it approximates this definite integral, right, this area under the curve, using the methods that we've been using before, right, just finding areas of shapes that we kind of already know. We're going to find the area of those shapes and we're going to kind of guesstimate the area under the curve, right? So how this works is what you're going to do is you're going to try and fit rectangles in the space under the curve, right? So let's say that I want to take a Riemann sum using two rectangles, right? If I wanted to use two rectangles to find the area of the curve between -5 and 5, I can just split that area down the middle, right? So I could use two rectangles that looks something like that, right? I can use those two rectangles. I can find the area under the curve of those two rectangles, right? And so basically what I would do, I would take the area of the red rectangles and then I would just sum them up and that would kind of be my estimation, right? As you can probably see, I have this area right here, right? That's not actually under my curve. So I don't really like that. Maybe I want to get my Riemann sum to be as close to the actual area under the curve as possible. And so far, if I only use these two rectangles, you can see that I have a lot of extra area that isn't actually under the curve, right? Okay, so let's say that instead of using two rectangles, I'm going to use four rectangles, right? So I'm going to cut my interval up in half again. So I'm going to take quarter intervals, right? So this right here would be -2.5, for example, and here would be 2.5, right? And so now I'm going to take smaller rectangles, right? So my first rectangle is going to be from -5 to -2.5, right? So that rectangle is going to look something like that, right? And I'm just going to keep drawing these rectangles in, right? So my next rectangle will be from -2.5 to 0, then from 0 to 2.5, and then from 2.5 to 5, right? And so now you can see that compared to my other diagram where I only had two rectangles, now that I have four rectangles, the area that's not under the curve is a lot smaller, right? So I only have like these small pieces now that have kind of like they have this extra area, right? So I'm going to keep going like that. So that's kind of what the idea of a Riemann sum is. The actual application of it is just find the area of all of your rectangles and add them up, right? So my point with this picture is I want you guys to notice how like the more rectangles I used, the smaller the amount of extra area I had, right? So now I want to ask you guys something, and it's what happens if I do 6 rectangles? Okay, what happens if I do 10 rectangles? What about 100 rectangles? How do you think that's going to affect my estimate for the definite integral between -5 and 5 for f of x, right? So that's all I have for you guys today. I really hope you think about this question and come visit me during session, and we can talk about it. So I hope you learned something. Thank you for watching.